Welcome to September 12th LeetCode Challenge, Reachable Nodes in Subdivided Graph. You're given an undirected graph, the original graph, with n nodes labeled from 0 all the way to n minus 1. You decide to subdivide each edge in the graph of the chain of nodes, which with the number of no nodes varying between each edge. The graph is given as a 2D array of edges, where edges at index I is the composed of these composed of U, V, and count. Indicate that there is an edge between U at I and V at I in the original graph, and the count at index I is the total number of new nodes that you will subdivide the edge into. Note that count at I is equal to 0 means that you have not subdivided the edge. To subdivide the edge of U and V, replace it with count plus 1 new edges and count new nodes. The new nodes are x at 1, x sub 2, and all the way to x sub the count. And new edges are this expression here. In this new graph, you'll want to know how many nodes are reachable from the node 0, where a node is reachable if the distance of max move is less or less. Given the original graph and max moves, return the number of nodes that are reachable from the node 0 to the new graph. Alright, that was a lot of words there. This to me sounds like basically a graph theory type problem and involves a lot of mathematics. That's exactly what it is because it's hard, right? You need to have a strong graph theory background to understand this question. But my first approach, or the first two things that come to my mind, is breadth first search in order to traverse through a graph and in order to assess the parameters I'm looking for. Or we could use a priority queue with Dijkstra's algorithm. So those two things itself are hard to know because you need some background on those in order to apply it onto graph theory for subdivided graphs in order to have reachable nodes. Let me try attempt to explain to you guys how this works. So you're given a node which is encapsulated in an array which has an array of edges, right? So we have 0, 1, 10, and then you have 0, 2, 1. So these are basically of the form U, V, and the count, right? So basically we're given the original graph, which is 0, 1, 0, 1, 0, 2, 0, 2, the edges, 1, 2, 1, 2, and then we have counts in between, right? So we in between the 2, 0, and 1, we have 10 nodes in between, which is indicated as count. Likewise, we have one count in between 0 and 2, as mentioned here, and then we have two counts in between 1 and 2, which is what right here. So let's see. It's something that we should note is that it is an undirected graph, meaning that there's no directionality between these two right here. So it's kind of weird that they're putting it bidirectionally, but I guess we can go in both directions. And we're given the amount of max moves of 6 and n equal to 3. So the max move is basically defining the number of nodes that you could reach in terms of distance. How many reachable nodes from 0, where the nodes are reachable, is the distance between max moves, right? So that's in the new graph. So how many moves can you make in order to reach the number of reachable nodes? And n is basically the number of nodes labeled from 0 to n, where you can subdivide each graph. So over here, the edge subdivision are shown in the image above. So the nodes are reachable by the highlighted yellow. So basically, in 6 moves from each of the main nodes, you could reach the following yellow. So you have right here 1, 2, 3, 4, 5, 6. Or you can go this way 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There you go, right there. So these are all the reachable nodes you can get to starting from 0, n equals 0. So basically, this is and this is an example here. And for here, the 0 node is disconnected from the rest of the graph, so there's 2 clusters. There's actually not even a 0. The 0 node is not even connected. It's not even given on here, but it is separated from the rest of the graph, so therefore it only takes 1. The max output you can get is 1. Let's see your constraints. So you see a whole bunch of weird constraints here. So the min of n to the n times n minus 1 divided by 2 is a mathematical formula. Again, the length of an edge is obviously equal to 3 because you need to have and max a triangle for that to work. Between 0, v and u and v is between 0 to n. There are no multiple edges in the graph. Count is between those numbers, maximum is between those 2 numbers, and between those 2 numbers. Alright. Alright, there you go. So, I'm going to try my best. This is a really hard question, and Dijkstra's algorithm is not the most, wake up thinking of it. It's just something you learn in school, and it's kind of, it's an algorithm that, it's very popular and famous that everybody should, every computer science should know, but it's not really, it's actually applicable to this question because it's kind of node related. So, intuition wise, so we treat the original graph here as a weighted graph, where it's undirected graph. So we used Dijkstra's algorithm to find all the reachable nodes from the original graph here. However, it won't be enough to solve the examples because we also have to subdivide it again according to count, right? So this is the original graph, but also we've given each node in between as well as count. So we have 10 things inside, so we need to get, we can only partially solve it from the original graph. So we will travel along the edges in either direction. So starting with 0, we can travel either this way or this way because it's not directed. And we can keep track of how many times we use the max moves, right? Every time we do one, we just decrement our max moves, and then we just take away one of the counts in between the 2 nodes. At the end of this, we want to know every node that we could reach in the original graph. So we also have to have an increment counter to keep track of how many moves we could make possibly. Because in total, we can move to all 13 spaces, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, I think. That's how you count. Yes, I think. Wait. What are we returning? Return the number of nodes that are reachable from node 0 in the new graph. Okay, yeah. So we want to return, every node that was reached from the original graph plus the sum of the utilization of each of the edges. So Dijkstra's algorithm is basically used to find the shortest distance between our source and all our targets. And this is a textbook algorithm. Additionally, we define it as nodes and neighbors. So we keep track of how many new nodes from new subdivisions we can make from the original edge, where we have a used category. And then at the end, we want to sum up how many times we've used up an edge. So let's kind of use that to our advantage. So we're going to use a priority queue as well. I probably suck at explaining how this question works, but you have something called graph, and it's going to be a default dict. And then we're going to have it a dictionary. So in order to understand kind of a weight of a graph, we're going to define it as this. For edges, for edge and edges. See, for edge and edges, the category list right there. Edges. So we're going to do a for loop here, and we're going to define the weight of the graph. So we have, let's use the variables they have inside that was given. So u, v, and the count or the weight. and that's going to be an edge. So we want basically to define a graph at U at V to be the weight, and then graph at, because it's bidirectional, so every edge going from U to V has to be the same weight as from V to U. So therefore, this exists. This statement is true, right? And we define that to be true. And then that's it for that. So we define an edge with the weights. Next thing I want to do is define a priority queue. So I'm gonna call it a call it queue, I guess, or queue, a priority queue, and that's gonna be our set of. So we are gonna actually keep it doing from the so priority queue we add it to the end normally, but this time I want to add to the front, so it's gonna be negative max moves, and it's gonna take in 0 as a tuple. Next thing I want to do is let's see. We also want, actually I'm gonna, instead of Q, and call it PQ, priority queue. And then next thing I want to do is have a kind of like a visited or a used category. I'm gonna call it used or visited. Used. I'm gonna call it visited, and it's gonna be a set, visited set. Okay. Next, I'm gonna employ the priority queue in a while loop. So to do that, what this means is that basically I am going to redefine while priority queue exists, we want our visited and our node, let's see, to be we also use a heap as well. We should use a heap. And this is not going to be visited. It's going to be the distance between two nodes. I call it distance. Just between two nodes. And it's going to be heap pop. So heap q dot heap pop from priority queue, and then our heap is going to be negative heap. So if node is in our distance set, we're going to continue because we already have it counted, or is already visited. Else, what we want to do is basically have the distance at that node to be assigned to our what am I doing? It's going to be visited. Change it back. So it's going to be distance for each node in our visited. That's going to be our visited node set at I. And that's going to be our distance. And then for each child in our graph at the node, it's going to be a square bracket, we are going to do an if statement. So if child is not in our visited queue and our distance minus our graph at the node and the child, which is also known as neighbor, is minus 1 is greater or equal to 0, then we want to push that into the heap. So heap q dot heap push, and we want to push the priority queue, and we want to push reverse our, let's see, distance minus graph at node and child minus 1 comma child. Okay, that should work. And then to finish off this algorithm, we have our output. So output will be assigned to the length of our visited set. For edge in edges, we're going to do another for loop here. We assign u, v to be edge at 0, and edge at 1. And then we have the distance between u to v will be our visited set at u. If u is in visited, else we return 0. And then from distance between v to u, also the same deal, visited at v. If v is in visited, else 0. We have our output, which is going to keep count basically, or increment each time you find the min between the edges, edge at 2, or the edges between u, distance between u plus distance between v to u. So u to v to u, and we return output. Jeez, this is hard. Okay, what am I getting wrong? Set does not support assignment. Let me see. Let's see if that works. Submit. Please work. Alright, so let me kind of describe this code again. So for this part here, so each node is only visited once. So once we reached a node in our original graph, that means we could continue to increment our output. Then for this part here, let's see, distance minus graph of the node here is how much further can we move basically from this node whose weight we have to the new node if there's only one edge basically, where we have we take also we also keep in mind that v is we want to use the edges as well, right? And then for this part down here, at the end of each, we want to basically redefine u and v, so we can use the maximums of all the weights of all the new nodes. We don't want to find basically the max between u and v from one side of the nodes and the other side as well. They return output. So space time complexity is basically big O of e log n, where e is the length of the edges, times n, which is the integer of the count. Space complexity is big O of the edges. So how many edges do we have? Alright, that's it. It's quite a doozy. Alright, have a great day, guys.